This is the course on group theory.
Your part in core course 11, direct products and group actions. These two portions I'll be taking. So, in the second course of group theory, I'll be covering 2 units from your syllabus, namely the unit 2, which contains properties of external direct products, the group of units modulo n as an external direct product, group of units modulo n. This you encountered in the theory of rings. In the ring Zn, if n is a prime, then Zn is a field. But if n is not a prime, then the group of units modulo n, they will be the numbers which are co-prime to n. Those numbers. So those elements will be units in that ring. So that group of that unit with respect to the multiplication, usual multiplication, form a group. So that group is here told about. The group of units modulo n as an external direct product. Internal direct products, fundamental theorem for abelian finite abelian groups. Unit 3 contains group actions, stabilizers and kernels, permutation representation associated with a given group action, applications of group actions, and generalized Cayley's theorem, index theorem. Here, in Unit 2, our main objective will be to generate new groups from the existing ones. We have tried out doing the same in your first unit by introducing the automorphism groups. Okay, there in the first unit you are doing your automorphisms there. The main idea, main objective for introducing automorphism there was to generate new groups from the existing ones. Now you might be wondering that why do we need to generate new groups from the existing ones? Abstract algebra is is a generalization of the existing structures, existing examples. Okay, fine. So if those examples are not occurring naturally, why do we need to generate them forcefully? The reason is you need to study those things, structures, separately. Like say you can if you introduce automorphisms as groups, then you can study the functions about from a set onto it itself as a group, and you have all the properties of the group handy to you. So that is the reason. That is the reason. So if you generate new groups, then it will be easy for you to look at them, to study those things as structures, and you can actually discover that those things, like those functions between themselves, so those things is actually having a group structure, or whatever structure you may discover. So then the study of them will be more easy and elaborate. Okay, so that is why we want to generate new groups from the existing ones. So automorphism actually does the same. They generate new groups from the existing ones, but no systematic idea about, you have given two groups, then how will you generate a new one? Systematic idea has been provided for the purpose. The concept of direct products serves this problem. That will also lead our way to uncover the structure theorem for every finite abelian groups. This is what I was talking about. Bring in a new concept, and that will let you look at the other existing concepts from a new light. This particular concept, this external direct product, or direct product, actually direct product will give you a light, will throw a light to the structures of every finite abelian groups. So whenever you have a finite abelian group, you know exactly how they behave. Okay, you have a isomorphic copy to every finite abelian group, and that you will know like the palm of your hand. Okay, structure theorem tells everything about the group. Okay, so this is the result what we get if we study this external, if we bring in this concept of direct products. In unit 3, in the third unit, group actions will serve as a prototype for operations between groups and other algebraic systems. This will lead to identification. This will lead to the identification of the operations done on a vector space as mere group actions. Okay, so you can identify the operations on a vector space as group actions, and that we will study in third unit. Now let's jump into the second unit, direct products, and we start with external direct products. If we start with two groups in hand and want to generate a new one, the most natural way to achieve our goal is to first multiply them as sets and then try to impose a structure on the product set motivated by the existing structures. So it turns out that this process actually works, and the newly generated group is called the direct product of the existing two groups. Let us carry out the process in detail. So now if you can tell me, like we have two groups A and B, and they have two different operations. On A we have asterisk, and on B we have star. Let G be A cross B. So this G is our product set what we were talking about. So what are the elements of G? They are product pairs A comma B, where small a is coming from capital A and small b is coming from capital B. So those are the elements of G. Now on this G, you want to define a binary operation, which should be motivated from the operations from A and B. So A is in A, and B is in B. A is with asterisk, B is with star. Now, so elements of G are A comma B. Okay, these are elements in G. G is A times B. This is your G. Now I want to define something on G. So yes, A1 B1, A2 B2. This is the most natural way to do this, because we have operation defined available on A, we have operation available on B. No, no, no. You have this one. You have this one. I mean, what do you do? A1 comma B1 dot A2 comma B2. Now the easiest way to do this is component wise multiplication or component wise addition. Probably you are being confused that since I am using a multiplicative notation, you are thinking that it should be A1 A2 A1 B2 B1 A2 B2 B1 B2. No, there is no relation between A's and B's. They are completely different operations. This is not defined. AB is not defined. That doesn't work. So I am trying to define something. Had I been written this dot by using a plus, then probably you would have told me that this will be A1 plus. Plus means in A plus, so that is I am using star asterisk A1 times plus A2. So this should be in my first coordinate, and in the second coordinate B1 and star B2. That's it. Component wise addition. component wise multiplication. The multiplications what we see are not component wise because the component wise multiplications do not serve our purpose. For example, the component wise multiplications in matrices will not serve our purpose. We do matrices for a particular reason to solve the linear system of linear equations. That was the very first thing. And there, if we define the product of matrices as component wise as we do the addition, then it will not serve our purpose. The component wise multiplication in case of complex numbers will not serve our purpose. That is why we define the multiplications in some other way. But when we start defining something, this is the inception of the entire concept. Here we are starting the thing. Why will we make our life complicated? We start with the easiest one. We start with the easiest one and then see whether that serves our purpose. If it does, then well and good. Otherwise, look for other ways to define things. So this is the entire idea behind this thing, that we should start with the easiest one, see whether that serves our purpose. If it does, well and good. Otherwise, look for alternate definitions. So let A and B be two groups, A with asterisk, B with star. G is equal to A cross B. Then this G is a product set. Now, keeping the essence of both the groups A and B, the easiest way to impose a structure on G is for any two elements A1, B1 and A2, B2 from G, define the binary operation the following way, as we discussed there. Operation component wise multiplication, operation on A in the first component, operation on B in the second component. Now let us examine whether this works or not. Means whether this operation makes G a group or not. Okay, that is what we want to check. This is a pretty straightforward exercise actually. Okay, closure and associativity work in G as trivial consequences of the same properties in the groups A and B. I want you to check these closure and associativity. Closure of this operation in G. So A1 B1 dot A2 B2 will be is A1 star A1 asterisk A2 B1 star B2. So A1 asterisk A2 is again in A because this is closed in A. Star is closed in B, so this product is also again in B. So this product is again in A cross B. So that is closed. Associativity again works. You please check this. You take three elements A1 B1, A2 B2, and A3 B3, and check using the associativity of asterisk and star. You check the associativity of this dot defined over G there. Okay, they come as trivial consequences of the same properties in the groups A and B. The obvious choice of the identity elements from each of the groups, EA and EB. Okay, EA is the identity of A, EB is the identity of B. This thing serves as the identity element where this line has gone down, where EA and EB are respective identity elements from A and B. Okay, you see, if you put EA and EB over here, then it will be EA times A2, EB times B2 over here. So EA times A2, that is A2, EB times B2 will be B2. So it will be A2 B2. So this is your identity. This is your identity element into A2 B2 is equal to A2 B2. Same will be the case from the right side as well. So that is the obvious choice of the identity element EAEB. Okay. Now the obvious choice for inverse of an element is A inverse B inverse. For any element A, B in G, the obvious choice of A inverse B inverse serves as the inverse element, where A inverse and B inverse are respective inverse elements of A and B in the respective groups A and B. A inverse is the inverse of A of the element A in the group capital A. Okay, so this element is being generated by the group by the operation asterisk, and this B over here, B inverse, is being generated, is the inverse of the element B in the group capital B, and that is generated by the star operation on the group capital B. So these two are quite differently generated elements into different groups. But in G, in A cross B, this serves as the inverse element. You multiply AB with A inverse B inverse, you get identity element back. What is the identity element? EA and EB. Hence, G is a legitimate group. So our first effort of defining things in the easiest way have worked. So we do not need to do it in any other complicated way. We have constructed G as A cross B from outside, externally. We have taken two groups A and B from nowhere and have merged them to create G. So for this reason, we call this particular thing as external direct product. Okay, this whatever we did so far, this G is called external direct products of the groups A and B. In this, the things are defined in the same way as we defined earlier. So this is called external direct product. Now, a few remarks. This definition can naturally be extended for any finite or even infinitely many groups. G1, G2, G3 up to G infinity. I mean, it goes on like this. So you multiply them in the product set component wise. Multiply them component wise. So it will be another infinite component element. So no problem. So we can define this thing in infinitely many groups as well. Assuming the maturity of the reader, that is you, the following abuse of the notations is often practiced. Okay, obviously we are not going to use this star and asterisk every time. We are going to remove them. Just A1 B2 for A1 B1 and A2 B2 in G. A1 B1 A2 B2 is equals to A1 A2 and B1 B2, and it is to be understood that the multiplication of operation over here is different as the multiplication operation over here, which is different from each of the multiplication operation over here. Okay, so this is the notation we are going to use from now on. All right, we have grown up seeing these kind of notations. Examples. Consider the group R plus. The external direct product of R plus with itself is the group R2 plus, where the addition in R2 is defined component wise. We can also take n copies of R and identify the external direct product of all of them, R cross R cross R, as the group Rn plus, with where addition in Rn is defined again component wise. The construction is also valid for infinitely many copies of R. Okay, this is an example of external direct product. Now, so anything of this kind will be like say Z2 cross Z2, the client 4 group. That is an example of external direct product. So So these things are there. Now, next example is a little bit not so organic example, but this example I have included to show that this operation can be as general as possible. So consider the groups, the set of all integers with respect to addition, set of all S3, set of all permutations with three elements with respect to composition of mappings, and set of all GL to R, that is set of all invertible 2 by 2 matrices with real entries with respect to multiplication. Okay, so consider these groups with usual operations. Then G as the product of all of these sets, A cross B cross C, is a group under the binary operation defined as this way. So n is an integer. So this is an element from G, A cross B cross C. N is an element from is an integer. Sigma is a permutation in from S3, and ABCD is a invertible 2 by 2 real matrix. So this is one entry. The second element in G is n, which is an integer, tau, which is a permutation, and PQRS, which is a matrix. So these are my two elements from G. And how do we multiply? We multiply in the first we multiply component wise. In the first component we have m and n. How are they multiplied, or how are the binary operation defined there? With usual addition. So this is m plus n, addition of two integers. Next we have elements from sigma. So how are they multiplied? They are multiplied by composition of functions. So this is sigma composition t. Okay, this is just function composition of function. So sigma compose t. So that goes in the second coordinate. In the third coordinate, we have elements from GL to R. So they are there. The binary operation is matrix multiplication. So here we have the third component as the matrix multiplication of these two matrices, the product of these two matrices. So this is my entire definition of the entire product. Okay, so this example is to show that this can be pretty general as well. So the proposition with this we will end today. Let G1 to Gn be groups and G is equal to product of them. Then order of G is the product of their individual orders. Product of their individual orders. Okay, number of elements in G will be number of elements in a product of number of elements in every one of them. If order of any of the GIs is infinite, then so is of G. Okay, proof is left as a homework. Please try to give a formal proof of this proposition.